Now, digital bandpass Butterworth. Use the specification in equation 7.34. Fs 8 kHz, Fp 2 and 3 kHz. We should have two passband because it's bandpass filter. And delta F being equal to 400 Hz, AS 40 dB, and AP 0.1 dB. Now, running the program inside Part5. Okay. The degree is reported to be equal to 11. And here you see bandpass form from 2000 up to 3000. No repels inside passband and stopband areas. Two stopband area, very natural for bandpass filter, and one passband. Okay. Now, again, the details, declaration of the parameters. Now, two stopband frequencies are reported to be the first one, FP1 minus delta F, and the second one, FP2 plus delta F, based on the definition for bandpass filter. And this time having WP containing four components. The first one, FP1, FP2, FS1, FS2. Okay? Now, N and WN are computed from signal.but.org, WP, WS, APAS, analog false. This will be the same for all four types. But computing the num and denom from butter, N, WN, B type band, and analog false. And the rest is similar. Now, designing band stop Butterworth, use the specification in equation 7.35. Fs, again, 8 kHz. This time, Fs is equal to 2 and 3 kHz, respectively. Delta F 400 Hz, AS 40, AP 0.1. Now, going to pie chart environment in a sec. Okay. The degree 11 and the form stop band. Okay. Declaration FS1, FS2, delta F, Fs, and how to compute the passband frequencies. Fs1 minus delta F will be Fp1, and for Fp2, Fs2 plus delta F, and Wp and Ws similarly but ordered, but num and denom will be signal.butter in WN, okay, B type stop. So you have got familiar with four types design of type Butterworth, okay? Now, continuing the discussion, this time Chebyshev of type 1, okay? Chebyshev of type 1. Now, without running the program, no, just I'll run one of them, okay? Okay, running Chebyshev 1. the degree of the filter is equal to 6. And here you see the repel in passband, no repel in stopband, passband frequency, and delta F 400 has been reported. Okay, 40, 0.1, 2000 for cutoff, or passband. Of course, it should be corrected to passband, delta F, FS, NFFT, FS, WP, WS. This time, the estimation will be based on the syntax Cheb1 ord. Cheb1 ord. WP, WS, AP, AS, analog false will lead to N and WN. And what about the major design, nom and denom? Signal.Chebyshev. Okay, Chebyshev. N, WN, and between them AP. Repel in passband. And B type, low, analog false. Okay. And without running high pass, just showing the major syntax. This time 40, 0.5, 2000 for passband, delta F 800, FS 8K, FS, okay, FP, FS, and Cheb1 or the same manner, but for high pass you need to write high here as syntax and AP, and moreover band pass filter, okay, the declaration 2000, 3000, two passband frequencies, delta F 400, 8 kHz for sampling frequency, and NFFT similar, FS1, FS2, WP, WS, and Cheb1 or completely similar to what we have mentioned earlier, and B-type band, okay, using Cheb1 ord for estimation and design Cheb1, okay, Chebyshev for design, Cheb1 ord for estimation. I of the degree. And similarly for band stop filter, declaration, here you see, this time 2K and 3K have been used as stop band frequencies and computing FP1 and FP2, WP, WS, Cheb1 or similar syntax, but a stop for band stop filter. Now, Cheb1 or Chebyshev design has been finished. What about Cheb2? I'll run just one of them. Say, for example, low pass filter. Okay, so making ready the PyCharm environment. Okay, running the program. Right. Here you see low pass Chebyshev type 2 having repel in stop band frequency but no repel in passband, and the degree of filter. Okay, declaration 40, 0.1, 2000, 800, 8K, and FSWPWS, this time Cheb2 ord. And the same parameters appearing for the syntax, and for design Chebyshev 2. So this time N, the first parameter, and the second one AS. For Chebby 1, we had AP because we had a repel in passband. But this time for Chebby 2, we should have repel in stopband. So we need to declare it. So NAS and WN. And the type is low pass filter, okay. Again, analog false. And moreover, for high pass design, without running the program inside PyCharm, showing the code, again, similar declaration of the parameters, WPWS, this time Cheb2 OR again, and Chebby2 high, okay? So it will be high pass filter and band pass filter, two passband frequencies, and declaration again, Cheb2 similar idea, Chebby2 band, and for band stop, again declaration here you see, and Cheb2 OR for estimation, and Chebby2 taking the parameter B type being stop here, okay? Now, we'll move to elliptic design. Maybe you can predict what we are going to show. ASAP 2800, I will run the band pass only FS and FFT, writing FS, okay? This time ellip OR, the same setting of parameters, okay? But the design syntax is ellip. The first demand is low pass filter, so similarly we write the code, and high pass declaration and ellip OR similarly for estimation, and design using ellip and APAS, okay? Because we have a repel in passband and attenuation and repel in stopband. So you may compare the coding between them, but I will run the band pass filter, just I need to provide everything. Okay, let's run band pass filter, elliptic. All right. Band pass filter having repel in passband and stop bands. Okay. And the degree of the filter here you see. Without going back to lecture note, let me run band stop as well. Okay. This is elliptic band stop filter. Okay. Band stop, repel, repel in the first and second passband. Now, going back to lecture notes. Anyhow, band pass filter, ellip OR, ellip, APAS should both appear in the syntax, and band for band pass, and a stop for band stop. That's it. Very simple. No. Do for all types of IAR design. Change the degree of the filter from lower values up to higher ones and criticize the results. Increase, decrease the minimum attenuation and in stopband and report the results. Increase, decrease the maximum repel in passband. Increase, decrease FP, FS, and FS. Try two different delta of F for bandpass and band stop filters. Okay? You don't need to always have similar delta of F for bandpass and band stop filters. They could be different. So show the results. Try two different attenuation for stop band 1 and 2 in band pass filter. Again, they don't need to be equal to each other. Take different attenuations. Anyhow, if you want to learn, there are plenty of materials and stuff for you. Compare the results of these IIR filters with the results of FIR filters using the window and remez methods and mention the advantages and disadvantages of each in the comparison tables. Now, digital IIR filter design using pole zero placement. Just show your power of design here. Okay? Poles near the unit circle lead to large peaks in the frequency response domain, while zeros near or on the unit circle lead to minima. Okay? Therefore, simple filters can be designed by placing the poles and zeros in appropriate places of the Z-plane. Just putting zeros or poles, of course, simple designs. Otherwise, you need computations. Not the first. Low-pass IIR filter design using pole zero placement. We are going to start low-pass design. Okay. If the cutoff frequency is FC less than Fs over 4, we will have alpha being approximately equal to 1 minus 2 pi Fc over Fs. The low-pass digital filter scheme is defined by the pole zero placement method as follows. K, controlling the gain of the filter. Don't worry about it if you don't understand. Just look at this part, okay? K times 1 plus z minus 1. Where is the zero of the system? It's 180 degree or z being equal to minus 1. So again repeating, having a zero in the left part of the unit circle and vice versa for pole. It should appear in the right part. Just memorize the form of low pass filter. Ignore about K. It just controls the gain to start from 0 dB or 1. Okay? Now, it shows the idea. Just have a deep look here. 0 appearing in 180 degree because it's going to remove the higher frequency because it's low pass filter. So higher frequency should not have permission to pass. Meanwhile, amplifying the low pass frequency. So amplifying will be done by poles and preventing the pass will be done by zeros of the system. Here you see the frequency response. Low pass filter having permission to lower frequencies to pass, but no permission for higher frequency. Here, the Fs or sampling frequency is equal to 400. You are showing half of it, the maximum allowable frequency. Okay. We just explained the figure. Demonstrates low-pass IIR filter design using pole zero placement where sampling frequency is equal to 400 Hz and cutoff frequency is about 6.25 Hz. Okay? Now, if the cutoff frequency is equal to or between fs over 2 minus fs over 4 and fs over 2 for high pass design, we are mentioning everything for high pass, alpha will be roughly about -1 minus 2 pi fc over fs minus pi. The high-pass digital filter scheme is defined by pole zero placement method as follows. Again, controlling the gain, just for a moment, ignore about k. You see here, having 1 minus z minus 1, the location of the 0 is located at 0 degree. And vice versa for pole. It should appear near 180 degree. Alpha, okay? Here you see the idea. Having this time 0 right hand side of unit circle, but pole left hand side. Okay? And here you see the frequency response. High pass filter. No permission for lower frequencies to pass through the filter. Just explain the idea. The figure was related to having Fs being equal to 400 Hertz and Fc 193.75 Hertz. Okay. What about band pass IAR? A digital, of course, using pole zero placement method. A digital bandpass filter has a pair of complex poles in the form of P being equal to R times e to the power of plus minus j theta. Two zeros are also located at the positions being equal to z plus minus 1 to eliminate the frequency of 0 and pi, because it's going to be bandpass. So no permission for lower and higher frequencies. That's it. The radius of the poles, their bandwidth, and angle determine the center frequency of the passband. An approximation between R, provided that R should be greater than 0.9, and the bandwidth denoted by BW is defined by the following relation. R is approximately equal to 1 minus BW over Fs times pi. The angle is determined as follows. Theta will be equal to F0 over Fs times 360 degrees or 2 pi radian per second. Or, no, I apologize, radian, because it should be dimension. No time. Radian per second is for analog time prototype. The relation between the center frequency F0 and two cutoff frequencies FC1 and FC2 is as follows. The center frequency will be equal to a square root of FC1 times FC2, and also the bandwidth BW is equal to FC2 minus FC1. Of course, it should be greater than 0 because we cannot have bandwidth of negative value. Digital passband filter is defined as follows. Controlling gain for you yourself, h of z will be equal to k times 1 minus z minus 1 times 1 plus z minus 1, okay, over 1 minus r times e to the power of j theta times z minus 1 multiplied by the second term, 1 minus r times e to the power of minus j theta times z minus 1, or leading to very interesting result, k times 1 minus z minus 2 no term for z minus 1, okay, over 1 minus 2r cosine of theta times z minus 1 plus r2 times z minus 2. And here you see the shape of bandwidth, just two zeros as mentioned, and two complex poles. So the cutoff will be, you see here, what just have been computed. FC1 120 Hertz and FC2 130 Hertz with sampling frequency of 400 Hertz. Now, band stop. A digital bandpass filter has the following complex conjugate pole pair. Sorry, typing mistake, band stop. We just mentioned it. P is equal to R times e to the power of plus minus j theta. Two complex conjugate zeros are also in the following position. Z is equal to 1 times e to the power of plus minus j theta, which remove the frequency of F0, the radius of poles, their bandwidth, and angle determine the center frequency of the pass band. Sorry, stop band. It's just a copy and paste in LaTeX. It just happens from time to time. An approximation between R provided that R being greater than 0.9 and the bandwidth BW is defined by the following relation. R being approximately equal to 1 minus BW over Fs times pi. The angle is determined as follows. Theta will be equal to F0 over Fs times 2 pi radian. The relation between the center frequency F0 and two cutoff frequencies FC1 and FC2, the same style, okay? So we don't read them off. Digital band stop. It should be band stop filter is defined as follows. Just the last line. H of z will be equal to k times 1 minus 2 cosine of theta, z minus 1 plus z minus 2 over 1 minus 2r cosine of theta times z minus 1 minus, plus r to the power of 2 times z minus 2. And here the frequency response, band stop, and two zeros on the unit circle near the poles, okay, in green color, okay, but inside the unit circle, because the pole cannot be on or beyond the unit circle for causal stable system. We have mentioned it earlier. Now, we just mentioned the idea. Fs 400 Hertz, FC1 120 Hertz, and the next one 130 Hertz. Okay.